So in this video, I will try to give a brief introduction to the notion of Galois descent. I will not go into details of the every proof and all. Rather, I will try to state all the main theorems and what is the main result, and also try to give one example of how it is useful. Okay, so you can do it in few steps. The first thing is the easier thing. So you can do the this motion only for vector spaces. So I will first start with that, and then if time permits, I will try to uh, do the same thing for any more general objects than vector space. We'll see that, what I mean by more general objects. So let's start with one thing that uh, what is the notion of Galois? So maybe we can start with what is the motivation. So, so suppose there are. So let's take these two uh, R algebras. Both are of dimension 4 over R. One is the Hamiltonian, the standard one, and another one is the matrix algebra. Right? So and you can complexify them. That means you can just tensor them C, and you will get this is just into our tensor C over R. If you just extend the scalars to make it into C. And interestingly enough, this Hamiltonian algebra, if you tensor it with C over R, this will also be isomorphic to M2 C. One can show that. One of the reason I can tell you this happens because C sits inside each as a copy, because any element of each would look like something like this, right? With I, J, and K, they like they have their usual properties. So you can take any complex number and you can think of it as 0 times j and 0 times. So maybe you can take this as a small exercise, but it's not very difficult to show that H tensor C becomes isomorphic to this. So what we are seeing from here is, firstly, they are not isomorphic as R algebra. So and the reason is simple because one of them is division algebra and another one is not. But when you are going up from R to C, you are getting two things that are isomorphic. So yeah. So the natural question is, can we go back the opposite direction? That means if I have uh, two objects, can I get to know, say, or more generally, let me say in this way, that suppose you have a Galois extension. So let L over K be a Galois extension. For now, we'll just do it for finite Galois extension. And suppose you have some K object. K object can be any vector space, any K algebra, or anything. So for now, you can just take it to vector space because I'll be doing it mostly for vector spaces as of now. So yeah, so we can just take any K algebra or maybe K object. Let's call it W. So W be a K object, and we can make it an L object of same type. Same type means if it was a vector space over capital K, after the tensoring with L over K, we'll get a vector space over L. So we are going from down to top. But is there any way to go in the opposite direction? That means if I have L object, then I get to know some K object from which that L object comes. That is the question. And that is the notion of Galois descent. So descent means you are going from top to bottom. And so the main question is, let me state the question first. So more generally, we would like to understand the following: that firstly, uh, given an L object, so throughout my lecture, L over Q will be a finite Galois extension. So this notation will be my prototype for mostly. And this was the main question that we would like to address is given an L object, when does it come from a K object, as I said. Secondly, how to determine if an object B is L over K form, I will define what it means, of some K object E. So L over K form means another K object B, such that when you tensor it with A, sorry, when you tensor it with L, that becomes isomorphic to A tensor. For example, H and M2 are, or say H is a twisted, or H is a C over R form of the vector set, because when you tensor it with C, it becomes isomorphic to M2C. That so by that I mean L over K form. Lastly, this is the most interesting question. But what is the set of L over K forms of a K object A look like? So that means what? You are taking all the L over K forms of a fixed K object A. That set, how does it look like? Or more precisely, is there any relation of that set? So how is it related to the Galois group, which I will denote throughout my talk as capital G. So these are the few questions that we would like to uh, we would like to understand. And the answer to the third question is the most interesting one because it has uh, some relation with some cohomology. This is actually the main theory that I will state by the end of this talk. So yeah. So as I said, I've already given you an example, so I'm not going to spend more time on that. So let me first do it for just vector spaces to get a feel for what we are actually doing. Uh, so for vector space, I will just state the main theorem and try to give some idea of the proof. So here in this case, you can take an equivalent definition of L over K form. That is, so let me define. So let me use bunch of definitions first. So definition. Suppose you have a L space V. So for L space V, uh, K space W, uh, or maybe a K subspace W, such that a K basis for W is an L basis for V is called a K form of V. That means what? Your V is a vector space over the bigger field. And you are taking a subspace that is over the smaller field W, and so that subspace will have some K basis. So if there is just one such K basis, is that when you view it as an L basis for V, or when you view it as, if you can view it as an L basis for V, it's a K form. So this So this kind of involves the choice of such a basis. So the next thing is the obvious one, that this choice actually doesn't matter. Meaning that here in the definition I said if one such basis exists, then every k basis of W will be an L basis for V. So we just take it in short that this choice of basis doesn't matter. In fact, the following are equivalent. This is really easy to prove. So first thing, as I said, every k basis of V is an, or sorry, every k basis of W is an L basis of V is equivalent to showing some k basis of W is an L basis of V, and thirdly, uh, W in the tensor it with L over K becomes isomorphic to V via this map. When you take a simple tensor like this, it will just go to an isomorphism of vector spaces, of L vector space. And these are really easy to show. For example, 1 implies 2 is obvious. And if you have a k basis, you can call it EI of W, so that it's an L basis for V. Then this map, that's the last map, say you have to choose an isomorphism. So you have EI as an L basis for V by virtue of 2, and also you have one tensor EI as a L basis for the left hand side, that is W tensor. And by this map, it takes that one tensor EI to EI. So that means both of them are bases. And the linear map is taking one basis to other, meaning it's just an isomorphism. And to show 3 to 1, it's again the same argument basically. Uh, you just take any k basis for W, call it EI, and by this map of 3, that one tensor, that EI, will go to EI. So because it's an isomorphism by 3, a basis will have to go to another basis. So EI is an L basis for V, because in the left hand side it was already a basis. So yeah. So these three are really easy to see equivalence relation or equivalence techniques. Let me give a bunch of more definition before we come to the main statement. So, and this definition will be valid for my next few propositions and all. So, let me put this definition as well. So, you have a as I said, the yellow work is a finite Galois extension, the Galois group G, and you have a L vector space V. So, we'll define it's called a semi-linear action. So, a semi-linear action, of G on a L vector space V satisfies. So you have any scalar from L, any element from this V. So it's an action. So sigma will act on this, and it will have this extra property that it's not a linear, so it's not taking the lambda out, but it's just twisting it by a factor of sigma. So when lambda becomes an element of the base rule, it behaves as usual as a linear because sigma fixes the elements of k, because sigma is an element of the Galois. So as an example, you can show that this action of G on W tensor on the second component is one such example. It's really easy to see. And we'll say an L vector space has a G structure if there is a semilinear action of G on V. And the main theorem, so Let me state the main theorem. So the main theorem says that there is a bijection. So main theorem says that you have all the G structures on V and you have all the K forms of V. So these two sets are in one-to-one. How does this bijection look like? So you take a G, or so you take a V, so it's equal to the G action, which is semi-linear, and you just send it to the invariant set. In the opposite direction, if you have opposite direction map is obvious because if you have a K form, so it's W, and you just send it to W tensor of L. And here this W tensor L has a G structure because by the previous example, you can act G on the second column. But so to show this is a bijection, firstly actually we have to show a few more basic things that this map is actually well defined. By meaning that we have to show that firstly that invariant set. So to just give a brief idea of how this proof will go. So firstly we have to show this is a K form. So you can use either of these three conditions that I wrote before. So how to show them? So for that, what you have to do is, so it's actually easy to use the third calculation. So you have to show that this map from VG tensor L to V by just taking any V tensor L to L of V is actually an isomorphism. This is what you have to show. So you have to show both. It's a one and all, and it actually it's not very tough. It's kind of easy to show. It's one. Basically, you have to apply some sort of. So what does it mean? So you can just so if it is one, so what you have to do? You have to assume this is 0. You have to show this element itself is 0. I mean, this wi is 0. So you can actually use what is called. So you can also assume that these wi's are already k linearly independent because otherwise if it's dependent, you can remove such Ws because you can write one of the Wi as some combination of them. So you can remove all of that. And then you can also assume that this sum is of minimal length. In other words, if you have a sum of less than n terms, such that this linear combination is zero, that means each of the terms are zero. Or in other words, equivalently, you can assume that uh, all the LIs are non-zero. And then can assume all LIs. And then you just apply a sigma to it. And it will be just, remember it's a semi-linear action. So it will be sigma of Li. And now these Wi's are actually coming from the fixed set. So sigma will not do anything to it. So it's just like if you just subtract 1 from 2, you will get say summation Li minus sigma of Li. Just now, so we can do one more thing. So we have said you can assume all the Li's are non-zero. And you can do one more thing that you can also take one of the LIs to be 1 because all of them are non-zero. So you can divide throughout by one of the LIs, L0. So the first term will be that is I'm sorry, L1. So L1 will be 1. So you can also assume that. But now if one of the terms are 1, that means that term will be 0 inside that because sigma doesn't do anything to the base terms. So that means this sum will be of length at most n minus 1. But then there's a problem because because of the minimality assumption, this will actually force that sigma fixes all the elements. And this sigma is arbitrary. So meaning that these allies are actually coming from the fixed field of the Galois of K over L over T. So they are actually coming from the base. And now it's done, right? Because we have assumed Wi is to be independent over K. So if such Li times Wi is 0 where Li's are coming from K, that means by independent property, all the Li's have to be 0 and F is 1. So this is one part. You have to also show that it's a onto, right? This line. For that, you can do it by taking the co-kernel. In other words, onto means you have to show that its co-kernel is trivial. Right? So then let me give a brief. So let me denote this by the co-kernel. And you can show that the co-kernel also has a semi-linear G action by just obvious things. What you do, you take any sigma from the Galois group and take any element V plus the image, you add sigma to it, you define it to be sigma. But you have to be a bit careful because of the well-defined thing. But it's easy to check because if you have an element of in the image, let me call it this, and you're acting on this, so this will just be this, and sigma this. But W's are coming from the fixed field, so this is just this, and this is W times sigma. Okay, so this is again an element in the image. This is well defined. Right? Sigma takes an element in the image to an element in the image. So you can factor through the co-coordinate. And then it's just some computation. So we have defined semi-linear G action on the co-coordinate. There's also a trace map on V, which is just you take any V and you add by all possible elements in the Galois group and you take the sum over all elements. And then it's really easy to check that this thing is actually in the fixed set because it's a finite group. So acting by any other sigma prime will actually give you a permutation. So it's easy to check. And also this thing is inside is actually inside the image of this. Right? Because you can simply take anything one in the second factor and any element in the first factor. So that will be inside the image of that. Right. So if you induce this map to the co-kernel, denoted by trace bar. So this is really, it means this is just the trace of this is the zero, right? Because obviously, because we have seen we saw that any element in the trace of that element goes inside the image. So when you go modulo image, it's a zero. This is a zero. And now you can show that whenever on a vector space the trace map is zero, then the domain itself is zero. That you can show. Or in more generally, if you have a trace map from V to V, say that uh, V is non-zero, so it has a non-zero element, then there exists some A, so the trace of this AV is non-zero. And the proof basically involves some linear independence of characters, usual things. So yeah, so you can show that. And this will follow that the image is zero, that means the co-coordinate is zero. So if is on, right. So we have shown the map is actually well done. Now to show this Things are actually inverse of each other. These two lines. So it's not very difficult because see the proof is actually very simple. What you need? So you start with V, go to the fixed set, and you come back by tensoring over L. Right? So you have to show that this is isomorphic to V. But because VG is already a K form, and we have already shown this map is an isomorph. So this follows trivial. Right? And on the other hand, we have a W, a K form. We first extend the scalar where W tensor. It has a G structure by second component. So you can easily show that the fixed set is actually isomorphic to W tensor, fixed set of the Galois group of rings, which is just K. W is also what this is isomorphic. So it's really easy to show that these maps are actually inverse of one. So yeah, so this shows if these two sets are in bijection. Now to come to the main or the more general setup. So I will not do that in this video, otherwise it will be too long because there are so many things to check and so many definitions to do. I will just state the main theorem at the beginning. Uh, so I will not define each term in the theorem from now. I will define it later. So let me just state this theorem. So this next thing is actually regarding. So this is for vector space, as I said, so and for main theorem uh, is regarding say spaces or for tensors of type PQ. Okay. So what does it mean? It means that tensor of type PQ is nothing but an element of. So V is the K object. So tensor of type PQ means uh, basically it's an element in this space. So you first tensor V times and you tensor the dual of V two times. And this is actually isomorphic to the Hom V Q times, V P times. This is obviously because of that isomorphism. I think this is isomorphism. So if we go V tensor W star, this is Hom of W. So this is actually some form of a Hom of tensor adjunction property. Good. So tensor is the left adjoint of the Hom form. This I think follows from that. It's not very difficult to say. Yeah. And so let me state the main theorem first and give the details next. So again, there's a bijection. So there are two sets. There exists a bijection between the following two sets. So we look at all the twisted forms of V comma phi. Where phi is such a PQ form over L, and this cohomology, whatever that means. Yeah. And so this left hand side means, so let me just give you some brief idea about the definitions. So twisted form means, as I said, a twisted form of V comma phi is an object, K object. So V comma phi is a K object, and its twisted form is another K object, W comma psi. So that when you tensor it with, when you tensor both of them over L, they become isomorphic as L object, whatever that means. We have to define what does it mean by isomorphism of L objects, because here the only thing is not the underlying vector spacing because we have to deal with that extra tensor. So we have to make sure that the morphism also takes care of the tensor. And in the right hand side, it's mostly makes sense because G is the Galois group of lower K, specified group. And the automorphism means you look at all the automorphisms of V comma, all the L automorphisms of V comma phi. That means L automorphism means you can tensor by L to phi, and you can also tensor this phi as well. So I'll define next time. So you can define that. And also G has a natural action on that automorphism set by conjugation. So, yeah. And so that means the right hand side you can talk about the cohomology. You can construct the co-cycles and co-boundaries, and you can go co-cycle that one co-cycle modulo one co-boundary. So get the elements of the first cohomology. Yeah. And yeah, so this bijection also takes care of one thing that their left side there is one trivial thing that is phi comma phi itself because it's already a twisted form of itself. Right? So, and in fact, this is actually not all the twisted form, but twisted forms up to an isomorph. Because what we actually need in the beginning, as I said, so if two forms are already isomorphic over the base field, we don't need to do anything with that. So you can identify them. But if those two, so we will only talk about those twisted forms that are not isomorphic over the base field K, but they are isomorphic when you tensor it to L up. So these are really the isomorphism class. So there is this isomorphism class of V comma phi, and there is this co-cycle or the class of the co-cycle, the element of the first cohomology, the unique co-cycle. That means every sigma will go to one. So there's these two trivial elements, and you can show that under this bijection they correspond to each other, and it's really follows from the definition. You can see next time. Yeah. And one application, so let me just take that application. So for those who know, uh, there's a central simple algebra over a field K. It's just a it's just an algebra with the center being isomorphic to the base field K. And it's a characterizing property that every central simple algebra has a splitting field, meaning there is an extension uh, L over K, such that when you tensor that central simple algebra E over that big field L. It's isomorphic to a matrix ring over A. For example, C is a splitting field for the Hamilton because its tensor product is isomorphic to C. And yeah, so and you can also show. I mean, it's not very trivial, but one can show that one such splitting field is actually separable. So, and any separable field can be embedded inside a normal extension as well. So, it's a separable plus normal. So, you can talk about the Galois splitting. So, yeah, so a central simple algebra that is split by L of degree n. Degree n means when you tensor it with the splitting field, as I said, it becomes n of some that splitting field. That n is called the degree. So, yeah. So you can talk about this set. We call this central simple algebras of degree n that are split by L. So these are actually by definition the twisted L over K forms of M and K because when you tensor it, L becomes isomorphic to M and L. And so by this theorem becomes isomorphic to. But what are these? These are all so automorphism of phi over L means it's all the automorphisms of M and N. And phi is here actually an element of, we can talk about V tensor V2, the base field K, right? Because in the matrix things comes with uh, an algebra map, right? So you can talk about tensor of type, not exactly V tensor V2 Q, it's actually V tensor V2 V. The remember is a tensor of type 1 comma 2, and it's easy to show again that any automorphisms of matrix algebra is actually inner automorphism. So meaning that this set is actually isomorphic to this. So the automorphism of this thing is inner automorphism. So any automorphism of M and L, or in general any automorphism of a matrix ring. So its automorphism group is actually isomorphic to the GL of that L. Modulo you have to go by the center, because when two elements are in the center they give rise to the same automorphism under the inner automorphism. So this is actually nothing but PGL of L. So this actually gives rise to this nice characterization of central superposition. And yeah, so next I will go into details of these things. So there are more applications to these are one. There are nice examples in which uses this main thing. So and stuff.